Okay, so we've got the Rutherford atom, right? The Rutherford atom has a nucleus, right? Like we discovered a nucleus, right? And we've got electrons orbiting the nucleus, and we can imagine that that they're orbiting just like planets, right? But this brings up a problem, right? One of the problems is that when you accelerate an electron or any charge, and these things are accelerating, right? They're undergoing a centripetal acceleration. When you accelerate a charge, it must radiate radiation. Okay, for example, this electron, this atom here, has the negative charges here, and then when it's here, right, you've got the electric field around it here. That electric field oscillates and goes to here, goes to here, goes to here as it goes around, right? And this thing is continually putting out these electromagnetic waves. Therefore, the electron should lose energy and spiral in, but they don't. Right? So that's a major problem, right? Is that somehow any charge that accelerates has to actually radiate energy, yet atoms don't radiate energy as a matter of fact. You know, they must be able to sit without radiating energy. And they can radiate energy, but they don't have to, right? The second problem, this was a much bigger problem with the Rutherford atom, was that at this time they were taking these atoms and exciting them electrically, and they were generating these spectral lines, and every element had different spectral lines, right? In fact, who is it, Mendeleev, or was he the guy? Yeah, I think so, the periodic table guy, right? Okay. There were holes in the periodic table that were filled when they looked at the sun, right? Helium, the spectral lines for helium were characteristic and not seen on Earth, so they called it helium, which means sun element, right? A heliostat is a mirror that tracks the sun, right? Helios is the sun. So there are these spectral lines that make these patterns like that. And Bohr's model, or the Rutherford model, didn't explain that, right? Even worse, okay, they followed these patterns, right? There were the Lyman series. This is like ultraviolet. The Balmer were visible light, and then these were infrared, right? Because remember, we can only see, from about 400 nanometers to about 700 nanometers. So we can see this part. This is ultraviolet, this is infrared, right? They followed a pattern, and in fact, to make matters worse, I believe a German high school teacher named Rydberg, okay, actually came up with the numbers for this. Now, if you took chemistry, advanced chemistry, you'll see. I mean, these aren't those orbitals, right? But of course, we didn't know this, right? Okay. So the visible ones, and then the ultraviolet ones are actually transitions to the ground state, and then the other ones, the Paschen ones, are transitions to the third orbital. But anyway, we'll look at that in a second. But there it is, right? It's got this beautiful formula for it, right? So Bohr comes up with a model, right? And the model is this: only certain orbits are allowed. They are stationary states. Now, why they are stationary and why they are only allowed in those states, we'll get to it. It, by the way, has to do with the de Broglie wavelength, or the de Broglie wavelength of the electrons. Okay, and it also has to do with standing waves, and it has to do with probability. Okay, so only certain orbits are allowed. But he basically threw this out here, right? And then the electron transitions between these orbitals. If you can imagine the orbitals as like circles, which they're not. Okay, the electron transitions create photons. So for example, if an electron makes a transition from here to here, it gives off a photon, right? If it makes a transition from here to here, it gives off a photon with even more energy, right? And if it makes a transition from here all the way down to there, if that's an orbital, right? Okay, even more energy, right? So the bigger the transition, the more energy that the photon has, okay? Now, what's sort of interesting is that these are quantum leaps. In the common jargon, a quantum leap usually means something that's like a big change, right? But in physics, quantum leap means, and this is a bizarre thing, is that the electron is in this orbital, and it then appears in this orbital. We don't see it going to that orbital. It doesn't go down. It just goes from this orbital to this orbital, and there's no intermediate phase. It makes the quantum transition means an instantaneous leap, and we don't see it in between. Okay, maybe it's not instantaneous, but we never see it in between. And, you know, I'll just let the cat out of the bag. These things are standing waves. They're standing probability waves. And if you think about that big spring in the front of the room when we're setting up standing waves, there are no intermediate standing waves. It goes from one mode to the next, and there's nothing in between that's stable. Okay. So anyway, all these energy levels, right? The electrons, when they go from energy level to another one, they just give off photons, right? So these are the ultraviolet ones to the ground state. There's a lot of energy, right? This is an energy map. This is the visible light ones, and then these are the infrared ones, IR. Okay, this is visible, and then these are the ultraviolet ones. They have so much energy, they're on the high end of the spectrum, right? Okay, so these are the first two assumptions, right? That there's only these certain stationary states allowable, that the transitions between these orbits are what create photons. Okay, it goes from one to another, and the energy difference turns into a photon, a particle of light. Okay, so let's look at some example problems. These are off like IB tests, right? What's the wavelength of the first Lyman line? Well, here they are. This is the first one, the second one, the third one, the fourth one, right? So the first one is a transition from minus 3.4 to minus 13.6. So the energy released, we can just subtract these, right? 13.6 minus 3.4. The energy released is 10.2 electron volts, right? And then so what's the wavelength of a 10.2 electron volt photon? We can figure that out. So 10.2 EV times 1.602 10 to the minus 19th times 1.602. All right. This is, the energy of this thing is 1.634 times 10 to the minus 18th joules, right? And then, let's see, the wavelength is hc over E, right? Because E is hc over lambda, so I just switched them, right? So the wavelength is 6.626. You could use that shortcut formula too. Divided by this 1.634. All right, here we go. It's a 6.626 E minus 34 times 3 E8 divided by that number I just got. I'm getting 1.216 times 10 to the minus 7th, which would be I'd say about 122 times 10 to the minus 9th, or 122 nanometers. Ta-da. All right, let's take a look at the next assumption here. All right, so the third assumption of the Bohr model, or premise, or whatever, is that angular momentum is quantized. Okay, and Bohr had to quantize something, so he quantized angular momentum. Now, if you recall, angular momentum is the moment of inertia times omega, right? And if you've got a object, a mass, the lollipop equation for moment of inertia is just mr squared, right? And then if you recall, the angular momentum, or angular velocity, is just the tangential velocity or perpendicular velocity over r, right? So that's v over r, right? And then if we just cancel, we end up with Mr. V, mrv, right? So that is, the angular momentum is mrv or mvr, right? Okay. And then basically what he said was that the angular momentum is equal to nh over 2 pi. Okay, which grown-ups would write this way, n h bar, right? Where h bar is h over 2 pi. You end up dividing Planck's constant by 2 pi so much that they've created another constant just to confuse you called h bar. Okay, and there it is, right? Okay, so basically his thing was that the angular momentum is just nh bar, right? Now, you know, why did he say this? Well, the answer was in the back of the book. right? Do you ever do that? Do you ever like change something to get the answer in the back of the book? He knew what the answer was. The answer was that it was the Rydberg formula. He had to justify the values in the Rydberg formula, and so he discovered that this was how you do it. Okay. So anyway, there's your third, right? And then ultimately, you can simplify the energy levels, and this is right out of the data packet, right? So this thing's golden here. There's that the energy levels are the ground state divided by, in general, n squared. So if n is 1, if it's the ground state, if it's the lowest orbital, you put a 1 in there, and the energy level is negative 13.6 electron volts. And then the second one would be 1/4 of that, and et cetera, et cetera. Anyway, so let's figure out what is the energy level of the fourth orbital and the second orbital. Okay, so let's figure this out. Fourth orbital and the second orbital. The fourth of the fourth is equal to negative 13.6 eV divided by 4 squared. That's not too hard, is it? All right, so let's do this. Negative 13.6 divided by 4 squared. And I'm getting that is negative 0.85 electron volts. And then let's figure out the energy of the second is minus 13.6 eV for 2 squared. So minus 13.6 divided by 2 squared. I could say divided by 4. So this is, and you'll see those are the numbers that are on that little diagram that we just looked at. Minus 3.4 eV, right? Okay. Now, if we're going to go 4 to 2 transition, this is a downward transition, right? So this is an emitted photon. By the way, if the electron makes a transition from a lower orbital to an upper orbit, it's actually absorbing a photon. But this one's giving off a photon. Okay. It's because it's going from a high energy to a low energy, right? So the energy released is the difference between these two, right? So 3.4 minus 0.85 is, that's the energy released, right? Is 2.55 electron volts. And then what is the wavelength of that? Well, let's make it into joules, right? So let's see, times 1.602 e minus 19. So that is 4.0851 times 10 to the minus 19th joules, and then the wavelength is going to be hc over E, right? Was it earlier this year I realized I'd forgotten Planck's constant. It shook me to my core. Times 10 to the 8th. All right, let's see. Then I remembered it again very quickly. Times 10 to the minus 19th joules. All right, here we go. All right, so 6.626 E minus 34 times 3 E8 divided by the answer I just got. And this is 4.866 times 10 to the minus 7th meters, right? Which is 480, I'll say 487 times 10 to the minus 9th meters is equal to 487 nanometers. There we go. Yeah? Yeah. All right. So you'll see that's a type of problem that you'll see on, I don't know, I guess presumably on IB tests, right? Okay. Now, limitations of Bohr's model. The first one is that it works well for hydrogen. By the way, if you have singly ionized helium, you can solve it, right? But once you have helium, now you've got a 3-body problem, and this is a famously difficult one to solve. We can solve special cases of it, but not a general case. It's pretty hard to, right? I just read this science fiction book called The 3-Body Problem, so kind of an expert on that. Does not explain, there's a fine structure to these spectral lines. So if you look at them, There's also, magnetism will split them and all this stuff, right? Why certain lines are bright, it doesn't, there must be some probability thing going on. Didn't explain why molecular bonds occurred. Basically, the Bohr model wasn't complete, but it was the first fairly comprehensive model of a particular atom, right? The simplest atom. Remember, a hydrogen atom is just a proton and an electron doing a dance, right? But anyway, otherwise it generally it's applaud. There he is. Niels Bohr as a young man. All right.